A 250 milliliter hydrochloric acid solution has a pH of 1.92. Find the pH after adding 250 milliliters of 0.0105 molar sodium hydroxide. Okay, so to tackle this problem, we're going to need the concentration of the acid. We're going to get the moles of acid out of that, and then we're going to calculate the pH from either the moles of acid we have left over from subtracting the moles of sodium hydroxide, because it's strong acid, strong base, so the moles are just going to cancel because they'll neutralize each other directly. So depending on whether we have a surplus of acid or of base, it's going to decide what we do after. Let's start with our acid concentration. So that is going to be equal to 10 to the negative pH, right? And that's 10 to the negative 1.92. That was the pH we were given in the problem. And that gives us a total of 1.202 times 10 to the negative 2 molar. And we can actually see the concentration of sodium hydroxide is actually less than this. So we already know that we're going to have acid in excess after we finish the concentration. So we just have to figure out how many moles we have, and then we'll calculate the moles of the sodium hydroxide and do our subtraction. All right, so moles of acid then. All right, concentration times volume for that. And it's going to be 1.202. Oh, goodness. Sorry. My apologies. That was bad even for me. Okay, 1.202 times 10 to the negative 2 molar. And we had 250 milliliters, so that's going to be equal to 2.50 liters. And that's going to give us a total of 3.01. Oops. 3.01 moles. And the negative 3 moles. All right. So now let's do the base. I guess we'll switch colors to the base, because why not? So we have our concentration already, so we can go straight for our moles of sodium hydroxide, and we'll do it the same way. Concentration times volume. And here we had 1.05 times 10 to the negative 2. Wasn't written this way, but that's the same thing. And we also had 0.250 liters for a grand total of 2.625. 0.625 times 10 to the negative 3 moles. Okay, so we're just now going to calculate our pH, because we know that we have more moles of acid than we do of base. So what we're going to do is we're going to set up an equation that looks like this. We're going to have the negative log of our new concentration, and the new concentration of acid is going to be the difference between the moles of HCl and the moles of NaOH, and it's going to be divided by the volume of the two of them put together, because we've added 250 milliliters of more of solution. So we have 3.0. Oh goodness. Let's try that again. All right, so 3.01 times 10 to the negative 3. That's the acid, and we're going to subtract from that 2.625 times 10 to the negative 3. There's our base. So the difference between those, and then this is going to be divided by the sum of both their volumes. And we had 0.250 liters of acid. We will add to that 0.250 liters of base. All right, punch that in the calculator, and we come out with a pH of 3.12. And that's our final answer. Question number 3. A student titrates 30 milliliters of 0.165 molar propanoic acid with 0.3 molar potassium hydroxide. Find the pH after adding the following volumes of titrant, and then we've got a whole bunch of them to calculate. So this is obviously going to be a marathon question. So we're gonna just take each of these things in turn, one by one, and calculate them all. Okay, I'm sitting here with a full glass of water and such. I hope you are too. All right, so I'm going to put this up in the top. 0 milliliters of titrant. That is also equivalent to the what do you call it? Initial pH, right? That's instead of 0 milliliters if you prefer that. Okay, so and that means that we're just looking at whatever of the acid dissociates itself, and that's going to be according to the following expression. So C2H5 COOH. Yeah, that's right. Aqueous, and that's going to give the following. It's going to give its conjugate, it's going to give its conjugate base, AO minus, and it's also going to give hydronium ions, right? Also aqueous. All right, so there's our expression for what's going on here. Now we're given our concentration to start, right? We know that this is 0.165 here, right? 65 molar, and these are going to be nil and nil, respectively, right? And we know this is going to be minus x, and as a result, this is going to be plus x, and this is also going to be plus x. Whoops. That was bad, even for me. Plus x, and that's going to give us totals of x, and 0.165 minus x. All right, there's our ice table drawn out here. So now we could put all these together with the values, right? I've gone the long way around with the ice table, but I'm going to show you that we could easily abbreviate this thing in the first case because we only have one source of ions. So if you've practiced a bunch of these questions, you would know these are always equal to this. It's going to be the square root of the dissociation constant, that's Ka, times the initial concentration of acid. All right, I suppose those parentheses were needless, but anyway. So it's always equal to this expression, but we'll do it the long way here, so you can see it proven in case you're not convinced already. And I'll take another color yet for that. All right, so we're going to write our expression here. We have Ka is equal to the concentration of the products, which is I'm going to abbreviate these. You've seen how bad my writing is, so you're with me, I'm sure. Conjugate base and the hydronium ions, and that's over our initial concentration here. Okay, and the Ka value for propanoic acid, which wasn't given in the question, but I know you can get it out of the same textbook I did. So that's going to be 1.3 times 10 to the negative 5, I believe. Yeah, to the negative 5. All right, and that is equal to, and these are both going to be x per the ice table above, so that gives us x squared, and we're dividing that by 0.165 molar minus x. All right, so we're going to assume first that x is small, right? So that means we can scrap x altogether, and we're going to take the square, we're going to multiply 1.3 times 10 to the negative 5. We're going to multiply that by 0.165. And that's going to be equal to x squared. And so we can solve for x then as the square root. Oops, sorry. You know what? Actually, let's move all this over here because I can tell I'm running out of space. So x is equal to, there we go. X is equal to the square root of, we got 1.3. 1.3 times 10 to the negative 5. And that's multiplied by 0.165. All right, and this is our, whoops, this is the, sorry, let me get rid of those. Whoops, not that much. Here, put that back on. All right, so this is our Ka value here, and this is our initial concentration of the acid. So you can see how these two expressions are the same, right? So next time we come up with one of these, and we'll just skip straight to this one here because we won't need the ice table at all. So anyways, we evaluate this thing, and it comes out to, see, I have it written down here somewhere, 1.465, oops, 1.465 times 10 to the negative 3. All right, so to check our small x approximation, we're going to divide this by our initial concentration first to see if this equals 5% or so. Okay, so I'm just going to do that quick. 465 divided by 165. Right, and I'm getting 0.8%. All right, this is like 0.88% or something like that. All right, so we're fine for the small x approximation. That's no problems whatsoever. All right, so that means that we've got this 1.465 times 10 to the negative 3. We're going to keep that as our x value. That is good to go. All right, 1.465 times 10 to the negative 3. All right, so let's make some room here. Oh my goodness, hang on. That eraser's huge. I need a smaller one. All right, there we go. That's going to do. All right, so get rid of that. There's some calculating room. And I'll leave that value at the bottom there. All right, x value, perfect. Now that we didn't have much more to do with this anyway, but why not? So now we just need the pH because that x is obviously equal to our hydronium concentration. That's where our pH is coming from. So we'll write it over here. pH is equal to the negative log of the hydronium concentration. And there we have it. So that's negative log of 1.465 times 10 to the negative 3, excuse me. And that thing gives us a total of 2.83. 2.83. So that is that's our pH before we've added any titrant in this at all. So that's also our initial pH. Okay, so next we are going to do the when we have 5 milliliters of 5 milliliters added. So I'm just going to get rid of all of this here. All right, all of this here. Okay, and whoops, also, yeah, get rid of that up there too. Okay, so now this is going to be after 5 milliliters. So let me change the value up here. 5 milliliters. Okay, so after 5 milliliters, because we're doing a weak acid titration here, this means that there's we're assuming a small portion of moles of potassium hydroxide are going to convert the acid into its conjugate base. And that's going to create a buffer solution, which we're then going to be evaluating. So let's write that out just so that we can see what we're dealing with there. So C2H5COOH. And now we're adding some hydroxides. We'll add that here. Hydroxide, these are all aqueous. Not like you can read that anyway, but... oh, whoops. And that's also not that. That's going to be a one-way street of a reaction. Okay, so we're going to have a portion of the converted base and some water as a result of the conversion. So that's going to be liquid. Okay, so and then we can use the Henderson-Hasselbalch equation to evaluate this one here. So let me change colors again. Well, actually, no. I guess we should do a little bit of it. But since the potassium hydroxide is a strong base, then there's not a dissociation constant to deal with. So however many moles of the potassium hydroxide we have, that's how many moles of the. So how many moles of this we have, it's going to be equal to how many moles of this we have. Right, that's good. Those are going to be equivalent values. So let's first find the amount of moles of potassium hydroxide we have. All right. So moles of potassium hydroxide, we were given the concentration. It was 0.30 molar. So we're going to get this from the concentration times the volume. So 0.3 molar. And we're adding 5 milliliters, and that's going to be equal to 0.005 liters, giving us a grand total of 1.5 times 10 to the negative 3. That's how many moles of potassium hydroxide we have. Okay, so we need to know how many moles of acid we started with, right? Because we're going to be evaluating the difference of this. So let's find the moles of our acid, HA, so I don't have to keep writing the propanoic acid formula over and over and over again. All right, and this was 0.165 molar, and we had 30 milliliters of this, I believe. Yeah, that's right. So 30 liters there. And that gives us a grand total of 4.95. 95 times 10 to the negative 3 moles. Okay, so we have more moles of this than we have moles of this. Okay, so that means that we're not going to be going past the equivalence point here. Like we're going to have more moles of acid than base and such. So that means that we're still on track to use the formula that we're planned on. So that's good news. Okay, so let's put this all together. So we're going to write this as the pH is going to be equal to, and Henderson-Hasselbalch is just pKa plus the log of, base over acid. And because we have the same volume, like the same volume that they're combined in for each, that means that we can just write the molar values here. We don't need the actual concentrations, which is lovely. Okay, so pKa, that is going to be the negative log of our Ka value. So negative log of 1.3, said 1.3 times 10 to the negative 5. That's going to give us that. And we're going to add on the log of. Now the way that we're gonna get this is the moles of conjugate base, and that's going to be equal to the moles of potassium hydroxide. That's a 1-to-1 ratio. So we can plug. There we go. Sorry, we can plug 1.5 times 10 to the negative 3 in up here, just like that, and then in the denominator, we're going to have the difference between the moles of KOH and the moles of acid. So I said them backwards, but that's what you got anyway. So that's going to be 4.95 minus 1.5 times 10 to the negative 3 will give us that. And that is going to give us a total of, just give me a quick second for that. Log 1.3 times 10 to the negative 5. Okay. We're going to add to that the log of 1.5 times 10 to the negative 3 divided by 4.95 minus 1.5 times 10 to the negative 3. Okay, and that gives us a pH of 4.52. 0.52. So that's what we look like at 5 milliliters of potassium hydroxide titrate added. Okay, next, 10 milliliters. Now, 10 milliliters is exactly the same. Oops, I guess I didn't have to erase that equation, but oh well. So 10 milliliters is exactly the same, so long as the moles of potassium hydroxide are less than the moles of acid, right? Because you saw the way that I just did it with the difference in the denominator means that if that difference goes negative, then obviously that's not going to work. You can't divide it by a negative number in that equation. So let's first see the amount of the moles of acid that we had. Right, I'm just going to write that up here. Moles of acid that we had was 4.95 times 10 to the negative 3. So long as our moles of potassium hydroxide are less than that, then we can just use the same route and we don't have to change anything. Okay, so moles of KOH, and this time we're multiplying 0.3 molar by 0.010 liters for 10 milliliters. And that gives us a total of, where am I here? Well, yeah, of 3 times 10 to the negative 3. Okay, so this value here, this is less than this one. All right, so that means that we can use the same equation the same way that we did. So I'm gonna change colors and we'll punch all this in again. Okay, so we're gonna Hasselbalch equation. So our pKa, that's the negative log of the Ka value, 0.3 times 10 to the negative 5. And we're going to add to that the log of base over acid. Okay, so base in this case, again, like conjugate base is equal to the moles of KOH. So we have 3 times 10 to the negative 3. And we're going to divide that by the moles of acid that remain, right? Now, this amount of moles of KOH, that's going to neutralize like the same amount of moles of acid, right? That's why we're putting the difference of the two in the denominator. So 4.95 minus 3, right? I suppose we didn't really need to write that out, did we? Times 10 to the negative 3. And we're set. Once again, calculator comes out. Negative log of negative 3 and plus the log of 3 times negative 3 over 1.95 times 10 to the negative 3. And that gives us a pH of 5.07. There we go. Whoops, I just realized I never wrote it up top here, but that was 10 milliliters. 10 milliliters. There we go. 10 milliliters of titrate, and that's what it looks like. 5.07 pH. Okay, next. Now what do we have? 10 milliliters, half equivalence point. Okay. So at the half equivalence point, we define that as the concentration of the weak acid and the conjugate base being equal. And that allows us we can use the Hasselbalch equation in a very simplified manner at this point. Okay, so hang on, I got to make sure I don't repeat that same mistake. So this is half equivalence point. Half equivalence point. There we go. Some of the best writing I've done so far. Okay, and back to my favorite green color. So we can go straight for the Hasselbalch equation because that log that we take on the side of the two concentrations are going to be the same. So this is just going to end up equaling the pKa value. All right, so log of base over acid. All right, so just write it without the brackets, but you know what this is about. Okay, so the pKa value, again, negative log of Ka, And that is 1.3 times 10 to the negative 5. And plus the log of the same concentration over the same concentration, right? So it doesn't matter what we put for these at all. So we'll just write x over x. It's going to give us what we want. So x over x, this is going to evaluate to 1. All right? Anything over itself is 1. And log of 1 is 0, right? That's the same as asking, 10 to the what equals 1, right? And everything to 0 is 1. So that means that this term is going to equal 0, and we're just going to be evaluating the pKa value. So pKa is 4.89, all right, plus the 0 from that gives us 4.89 total, and that's going to be our pH at the half equivalence point. All right, so this is a lower pH than the 5.07 that we just calculated. So obviously the half equivalence point was passed before 10 milliliters, but we're not calculating the volume at that, so no troubles there. Okay, next is the equivalence point. All right, so at the equivalence point, the molar concentrations of the acid and the base, analyte or titrant if you'd rather, are equal. So when you're looking at the graphs of the titrations, right, where we're plotting pH against the volume of the titrant, right, V-tit. All right, so we start somewhere up here with a weak acid because it's not as strong, so it doesn't start at the bottom. And this gradually comes up like this and then turns over and goes this way. This point right here where it changes directions, we call it an inflection point. Right? And if you remember from the calculus class that we just finished, this would be y over d squared x. That is when this is equal to 0. And particularly in this point, meaning that the second derivative before this was 1 and then change signs over it. Always fun to be able to be making connections like that. Anyway, so this here, because we're doing a weak acid titration, this means that we've converted the full amount of the acid into its conjugate base, meaning we're going to have, I think it was 4.95. We're going to have 4.95 times 10 to the negative 3. We're going to have this many moles of the conjugate base. So, and we don't have any acid or any hydroxide to contend with because they both neutralize each other totally, actually. So let's actually get rid of this, and I'll write the equation out beforehand. So because they've neutralized each other, the principal ionization source is going to be the conjugate base ionizing the water, since we don't have any acid or hydroxide ions anymore. So that means we're going to be headed for a Kb value and calculating things that way. So C2H5 COO minus, that's the conjugate base that we're left with. We know we've got 4.95 times 10 to the negative 3 of this. This is moles, not concentration. And this is going to dissociate. Well, not dissociate, but it's, oh, whoops, yeah, sorry. Hang on, sorry. I did this inside out. Excuse me. That plus the water. And that is going to give conjugate acid. Right, also aqueous. And hydroxide ions. Aqueous. And out of these two, hydroxide ions and the conjugate acid, hydroxide ions are a stronger ionizing force. So these are going to be the ones contributing to the pH. All right, so here we go. First, we need the concentration of our conjugate base, right? So it's going to be this total here, and that's got to be divided by however much volume we've got between the bits there. So let's calculate that first. So that's going to be 4.95 0.95 times 10 to the negative 3 moles, right? And now we're looking to put liters in the bottom. So the we can divide. We know that it took this many moles of potassium hydroxide to neutralize the acid, right? So that means that we can stick that straight in the bottom. 0.95 times 10 to the negative 3, and that's going to be divided by the concentration of acid. Right. This is using the this relationship, like that volume equals moles over concentration. That's what we're doing over here. Okay, so that, but we have to add to that the volume of acid that we had initially, and we had 30 milliliters of it, which we'll write in liters as such, right? So if we calculate this, let's see what we get here. So 1, 2, 3, 4, 9, 5 divided by 3 plus 5 divided by 0.3. All right, and I've got this. That's a 0.106452. Again, we're just taking a whole bunch of extra significant figures over what we need. Okay, so let's make some space here now that we got that. Whoops, actually, hang on a second. Well, actually, you know what? Here, this is a better way to do it. Need some kind of reasonable eraser size. Okay, let's get rid of this. If ever we do this again, I'm going to need one of those really cool like space age dual monitor setups, because I'm doing this in a tiny window on my MacBook, and it really just is. You really can't do this stuff with this small of a screen to look at. All right, so let's copy in that concentration here, 452. All right, now we can get rid of this down here for good. All right, water. Concentration obviously doesn't matter. All right, and we didn't have none of this. All right. And you may recognize this actually as the same table earlier that I said that I wouldn't be writing anymore, right? And we actually don't have to. We're just going to change it to writing this in terms of the Kb value instead. So Kb, we can get from Kw equals Ka times Kb. So we can write Kb as, good grief. Right, Kb as the quotient of Kw over Ka. All right, and we can stick this in that abbreviated equation that I showed earlier. So we'll do x equals the square root of, and we'll put Kw close enough over Ka. Also close enough. All right, and that's going to be multiplied by our initial concentration that we solved for. Right, so we can just put that straight in. 6,452. All right, and this is going to be equal to Kw is 10 to the negative 14. That's over 1.3 times 10 to the negative 5. All right, that whole thing should be in parentheses. All right, so we'll sort of put around it what we can. Hey, not bad actually. Times 0.106452. All right, and let's evaluate that thing. Okay, that gives me 2 seconds here. So it's 3 and times 0.06452. Okay, I am getting 9.049. 9 times 10 to the negative 6. Okay, so this is a smaller value even than we evaluated in the first step. If you remember that far back, we had something times 10 to the negative 3 that we were evaluating against like under 0.165. That's the concentration of the acid initially, right? And that was a small enough X value that we were able to approximate it. I mean, if you're, if you want to be absolutely sure, this over this, because this is 0.106, right? I mean, this is even smaller than the other 0.106. Yeah, that's so tiny a number I'm not even going to write it. Anyway, so that approximation is perfectly valid. And our P, this is given as X. That's the concentration of hydroxide ions here, right? So let's get ourselves a different color. And we'll get our hydroxide concentration from sorry, not the hydroxide. We'll get our hydronium concentration from the Kw divided by the hydroxides. That's sorry, to put that, that's this. So let's do it the official way. So this is equal to this, Kw divided by the hydroxide concentration. All right, and we know both these. The concentration of hydroxides is equal to this X value that we just solved for here, 9.049 times 10 to the negative 6, right? Kw we also know. So that means that we can solve for the pH by taking the negative log of that. So pH equals negative log of, so that's Kw is 10 to the negative 14. And we divide that by the hydroxide concentration, which was 9.049. Sorry, I should be using my math manners here. Times 10 to the negative 6. All right. So I'm going to put that in mess in my calculator. So negative 14 divided by 4569049. Okay, and take the negative log of that. And I calculate a pH of 8.96. 96. All right, and that's our pH at the equivalence point. Right, we have a weak acid being titrated with a weak base, so we're not surprised that the pH is north of 7. Okay, let's make some more room here and take on the next one. Now we're going to do 20 milliliters of titrant. I'm going to make this even bigger. So 20 milliliters of titrant, like if we didn't know the volume that at the equivalence point, right? But we just passed it, and I guess that wasn't exactly clear. So let me put that into. So I'm just going to write this up top. This is 20 milliliters. Try that again. 20 milliliters of titrant. Okay, so when I calculated the concentration of the conjugate base earlier, I had to add the volume of KOH required to get there, right? And that is equal to this, 4.95 times 10 to the negative 3. This is the amount of moles of base that we had, right? So it's going to be the amount of, obviously it was the same as the moles of KOH needed to neutralize it, and this was just divided by the concentration. All right, that is a 3Ms. Leave that. This gave me that many liters, right? 16.5 milliliters. So I know that, so 20 milliliters is obviously more than that. So that means that we're going to have hydroxide ions in excess. In excess when we put the, it's going to more than neutralize the acid, and we're going to be, and then it's going to be the hydroxide itself that's going to be ionizing the solution afterwards. So we can calculate this like this. Let's see. I think there's a shortcut for this too. All right. So the pH, we know. Okay. Well, we know that there's going to be more hydroxide than acid. So I'm going to be doing it this way. It's going to be the difference between 14 and the POH. Okay. And that is going to be 14 minus, right? And POH is the negative log of, right? And we're going to get, it's like the mole, we're going to subtract the moles of, moles of acid from the moles of KOH, right? So that's going to be, what was our moles of KOH is, sorry, that's a brain fart and a half. It's going to be 0.03. 0.3. There's concentration. All right, times 20. Sorry, not. Can't do 20. Need this in liters. Times 0.020 liters. Okay, so this little bit here, this is going to be equal to the moles of KOH. Yeah, sorry, this wasn't very clear at all. All right, from that we're going to subtract the moles of the acid that we already know to be present, which is this. All right, 4.95 times 10 to the negative 3. All right, and this is moles of acid. Okay, and then we're going to again divide this over the total volume. And so the total volume, we started with 30 milliliters of acid. Okay, so there's that, and we're adding to that 20 milliliters of base. So that's going to be 0.020 liters, like that. All right. Okay, so this beast is going to give us 0.3 times 2. 495 divided by 105. All right. And I've got a result of 12.32. 12.32. There you go. And that's 20 milliliters. Onwards we go. So now we're up to 25 now from 20, sorry, excuse me. And we're going to do this one exactly the same way as we just did that one. All right. Okay, so we'll do the pH is equal to 14 minus the POH. All right, same expression to start. And this is equal to 14 minus, and here we go again, negative log of. So it's a nice big bracket to work with here. Okay, so again, we need the moles of potassium hydroxide minus the moles of acid. All right, because it's like the moles of acid neutralize a bunch of the hydroxide, and obviously the only ones that are going to ionize are the ones left over from that. So we're going to find that again by concentration times volume. So 0.3 molar times, and now we've got 25 milliliters, so that's going to be 0.025 liters, just like that. Okay, and we're subtracting the moles of acid, which is again 4.95 times 10 to the negative 3. And that's divided by the total volume, which is now the initial 30 milliliters of acid plus the 25 milliliters that we have written over here. All right. And another fun calculator adventure is negative log of 0.3 times 0.025 minus divided by 1055. And that gives us 12.67, I suppose. 12.67. And there we have it. That is the pH after 25 milliliters. And that is the last that we had to do. Thanks very much. Question number 5. So 25 milliliters of 0.115 rubidium hydroxide is titrated with 0.11 molar hydrochloric acid. Determine the following, and we're given a couple different pHs and volumes to solve for. Once again, bit of a involved and time-consuming problem. So let's take all these things one at a time. Okay, so first we are starting with the initial pH, right? And just like the last titration bit, I'm going to mark all these in the corner. So this is the initial pH. All right, and to solve for this thing here, because rubidium hydroxide is a strong base, we can do this pretty simply. So this is just going to be the difference between 14 and the pOH that we can get directly from the concentration we were given. So 14 minus the pOH, just like that. And we're going to get 14 minus, and pOH we'll get from the negative log of our hydroxide concentration. Hydroxide concentration was 0.115 molar. All right, and so that's going to give us 14 minus the negative log of 0.15, and I've got 13.06. 13.06. All right, so there's our initial pH before we start any kind of titrations. All right, next we've got whoops. It's a big eraser to be missing things. Okay, next we've got the volume of titrant required to reach the equivalence point. Okay, so we'll put volume to reach the equivalence point. There we go. That'll do. All right. And here, because we're titrating a strong base with a strong acid, the ionizations are going to be complete. So we can get the volume just from like this thing here. 1v1 divided by second concentration, just like that. And so we'll do the RBOH one here. That's times 25 milliliters of that. And we'll divide this by the concentration of our titrant, which is 0.1 molar. And that's going to give us, quick second here, times 0.025 divided by 1. And we get, we'll put it in milliliters. We get 28.75 milliliters. 0.75 milliliters. And again, this is possible because we're dealing with a strong base and a strong acid. That's why we can use that. That's why we can use this method here to get it. But anyway, that's the volume of titrant we need. Okay, and next, we're looking for the pH after we add 5 milliliters. So put 5 milliliters up here. Okay, so pH after 5 milliliters. So we're gonna do exactly the way that we did it in the first place. Sorry, just give me a second. And to pull myself out of color here, it's easier to see. There we go. Okay. Now, so we'll do the pH is equal to 14 minus the pOH. So 14 minus, and I should actually say before this, I know that the pH is going to be 14 minus the pOH here. I know this is usable because 5 milliliters of titrant. This is way less than what it's going to take to get to the equivalence point. So we know we're going to have more moles of hydroxide than acid. So that should be noted here. Okay, so this is going to be the negative log of, and we need the moles of base. So that's concentration times volume, 2.5 liters. And we're going to subtract from that the moles of acid. So, whoops, okay. So this one's going to be volume times concentration. All right, molar, there's the moles. And we can divide this by the total volume between the two. So that much of the base, and we add 0.005 liters of the acid. And again, we can do this because we know that this many moles of base is of acid, is going to neutralize this many moles of base. So we can take the shortcut here. All right, just give me a second to put this thing together. So 1.5 times 0.025 minus 0.501. Okay, and I have got 12.90. That's the pH after 5 milliliters of hydrochloric acid is added. Okay, and next is the pH at the equivalence point. So this is definitely the easiest one of the lot. At the equivalence point, because we're dealing with a strong acid and a strong base, we're gonna have and the equivalence point, means that the concentration to the two have to, or the moles of the two, have to be equal. That means that we're gonna have no ionization taking place from either of these compounds, because even their conjugate ions form a pH neutral solution because they're a strong base and strong acid respectively. So this means that the only ionization happening is the auto-ionization of water. Which I guess we'll work it out. Why not? So auto-ionization of water is Kw, and that's equal to the product of hydronium ions and hydroxides. Obviously, there's water under here as one of the reactants, but we don't write liquids in here, so that's what it is. We know that Kw is 10 to the negative 14, so we can put that in. And we don't know what either of these are, so this is just going to be x squared. And so that means that the square root of 10 to the negative 14 is equal to x, which means that x is equal to, we'd write this as 10 to the negative 14 to the exponent 1 over 2. And since this is by rules of exponents, then we multiply the exponents to satisfy this, which means that x is going to be equal to 10 to the negative 7. And we calculate the pH as the negative logarithm of this concentration, and we can read the negative logarithm straight off it because this logarithm deals in base 10, which means that the negative logarithm is just going to be equal to the negative of the logarithm, which is 7. And there's our pH. That's the pH of the strong acid and the strong base at the equivalence point. A little more there than necessary, but why not? Why not? Okay, what's next? pH after 5 milliliters of titrant is added beyond the equivalence point. Okay, so we have we'll put equivalence point plus 5.0 milliliters. Okay, a couple screens ago, I did calculate the volume needed for the equivalence point. Perfect. So we'll add 5 milliliters to that. Now in this case, we're going to turn the equation around. I said that we were using the equation of this form. All right, this is worth looking at for a second. I said that we were using the equation of this form because we knew for sure that the moles of the base were larger than the moles of the acid. And so long as we knew this, then we calculate the pH this way, because we're going to have hydroxide in excess, and that means that it's going to be the one that's contributing to the ionization. So when we have equivalence point plus 5 milliliters, we know that this is not the case. Now we're going to have acid in excess. So that means that the pH expression is the negative log of our hydronium ions directly. And this is going to be equal to the negative log of, all right, here we go. So also we can abbreviate because we know that 28.75 milliliters just cancels out the whatever base ion or base moles there are there, right? So that means that the only moles that we have to calculate are the ones coming from the 5 milliliters over. So it's going to be 0.005 liters times 0.1 molar. But we do have to divide this by all of the volumes so far, which means that we're going to have a few of them. Okay, so first, the volume that we just add in addition to the equivalence point. Sorry, let me clean that up a touch. That's even worse. Third time's a charm. It is. Okay, so here's what we needed to get to the equivalence point. That was 2875 liters. And also what we started with. There we go. We have to add all that together in the denominator for this to work. Okay, give me a quick second to get you a total. So this will be the negative log of 5 times 1 divided by 5 plus 2875 plus. Okay, and that gives us a final pH of 2.07. 2.07. And there we have it. That's our final value that we need to calculate. Okay, so question number 2.1. Calculate KSP for the following. And we give all the molar solubilities in parentheses here. Okay, so to get started in this, we'll write out our solubility reaction. So we had nickel sulfide, right, and that's a solid, and that is going to dissolve into its ions. So we're going to have nickel 2 plus, this is going to be aqueous, and sulfur 2 minus. which will also be aqueous. Okay, so we start, if these things dissolve fully, then we wouldn't be dealing with KSPs in the first place. So we always know that this is going to be in excess, right? And then because it's a solid, we don't even calculate the rest of it. It is going to dissolve to give us X and X of this. There is no there's no number in front of this because each of these stoichiometric coefficients is equal to 1. And with these problems, these again abbreviate into something that looks like this, where you have n times x raised to the power n, where n equals the stoichiometric coefficients. So I'll just put that over here. Stoichiometric coefficients. All right. So anyways, we have 1 and 1, so that's not going to trouble us here. So when we go down to calculate KSP, so our solubility constant is going to be it's the product of these, the product of the products over the reactants, and we don't write the reactant at all because it's solid, so we end up with x squared here. And so we take the molar solubility that we were given, and that is going to be x here. So we just take the square of 3.27 times 10 to the negative 11, right, squared, and that gives us our result, and that's going to be 1.07 times 10 to the negative 21. And there it is, easy as that. All right, so let's do the next one now. So let's just erase all these things. Okay. All right. And new reactions and new color. All right, this time we're looking at lead difluoride. Okay. Sorry, excuse me. All right, so let's write out a reaction again. So we have lead, fluoride. This is obviously solid again. And this is going to give us lead 2 plus, and this is aqueous, plus 2 F minus aqueous. We're getting that 2 here from the 2 over here in the formula. Now this now gives us an opportunity to use that same abbreviation equation that I just pointed out, where we had nx to the power n to be written in the KSP equation. Sorry. So we're going to have x for here because there's only 1 for the stoichiometric coefficient. We will have 2x for the 2f, and that means that our equation is going to look like this. It's going to look like x times, we're going to use nx to the power n, and we're going to put in the 2 that we have with the fluoride ions. So we'll have 2x squared, and when we square this bracket here, we get 4x squared. 4x squared, and times the x, that gives us 4x cubed. All right, and now we just sub in the molar concentration. So we've got 4 times 5.63, 63 times 10 to the negative 3, and that is cubed. All right, and that gives us a grand total of 0.6. Okay, so 5.63 cubed times 4, and I've got 7.14. 4 times 10 to the negative 7. And there we go. And there's our KSP for this one. All right, last one. Last one. Okay, now magnesium difluoride. So magnesium difluoride. Again, obviously solid. We're dealing with KSP. That's not going to be anything else. That is going to give us magnesium 2+ in an aqueous solution. As well as, again, from the 2 in the subscript here, we're going to get 2F-. F-. Okay, so again, using our NX to the power n formula, we're gonna not look at that at all because it's solids. And the aqueous ones, we're gonna get X here, and we're gonna get 2X here, which means that we're gonna write our KSP expression as X times NX squared. And it's like X times, now we'll put the 2 in, 2X squared equals, first deal with your exponents first, your BEDMES or your PEDMES or however it is that you learn that. That gives you 4X squared times X is again 4X cubed. All right, long time no see. Okay, and this time we had 2.65, so 2.65 times 10 to the -4, and that is going to be cubed. All right, and that gives us a grand total of 744 times 10 to the -11. And there we go. That's it for question 2.1. Okay, question 2.2. Calculate the molar solubilities of the following. We're given 2 of them to do, so let's take each in turn. So we will start with silver bromide, and we're going to write, again, we're going to write out our reaction here. This is exactly the same question that we just did, but backwards, essentially. Okay, so Br, this is going to dissociate into Ag plus aqueous, obviously, and bromide. Aqueous. Okay, and this is solid here, so this is going to start in excess, and it's minus X or whatever, and we don't care about it for the rest of it because it's solid and it doesn't factor in the expression. We're going to add X and we're going to add X because the stoichiometric coefficients for each of these is 1. So that means we're going to get the following expression. From this, we're going to have the KSP is equal to X times X. So we get X squared. And in this case, we have a value for KSP as opposed to for X. So we're going to solve for X instead. So we're going to take the square root of both sides, making X equal to the square root of KSP. And the square root of KSP is, what is the KSP here? 5.35. 35 times, where am I here? 10 to the -13. 10 to the -13. Okay, so square root of that thing, where have I put my calculator? 5.35 times 10 to the 13, square root of that. And I'm calculating 7.31 times 10 to the -7. 1 times 10 to the -7. All right, so there's our first molar solubility. All right, next, we're going to do the magnesium hydroxide. Okay, I've lost my pencil. Oh, there we go. We're back. Okay. So magnesium hydroxide. Those there. Okay, and same idea here. This is going to give us magnesium 2+ in this case. Yes, and 2 hydroxide ions. Now you remember back to the last question that we just did. I said to keep this in mind, that we can abbreviate these in this case, and it saves us a lot of thinking. All right, so once again, we're not going to worry about this. Stoichiometric coefficient from magnesium to magnesium hydroxide is 1:1, so this is just going to give us X. And this here is 2:1, so this is going to be 2X. 2X, which is going to give us totals of X and 2X in these two cases. Meaning our KSP expression is going to look like this. KSP equals X times, and now we're going to use this formula directly without writing it in the general case first. 2X squared, with 2 being our n value. And we're going to solve the exponent first. It's going to give us 4x squared, and then multiply it by the x for 4x cubed. Now, once again, we have a value for the KSP as opposed to the molar solubility x. So we're going to solve for x here. We're going to divide both sides by 4 and then take the cube root to isolate x, meaning that x is going to be equal to the cubed root of KSP over 4, like that. Okay, and the KSP value was, where am I here? 2.06 times 10 to the negative 13. 6 times 10 to the negative 13 before cubed root, and I get back 3.72 times 10 to the negative 5. And there you go. There's the answer. Question 2.3. A 150 milliliter solution contains 2.05 grams of sodium benzoate and 2.47 grams of benzoic acid. Calculate the pH of the solution. Ka equals 6.3 times 10 to the negative 5. Excuse me. Okay, so this is going to be a common ion problem. And we know what we have. We know we have benzoic acid. We know we have sodium benzoate. So first, let's figure out how many moles of each we have, and then we'll figure out how we're going to write this thing out. Okay, so let's start with sodium benzoate. So the compound looks like this. Let's see, 6H5 COO, and then sodium tacked on there. Okay, so let's find how many moles of this we have to start. So moles of that is going to equal the mass divided by the formula weight. Okay. It's been a while since I've written that. Okay, and this is 2.05 grams of this that we had. Okay, and then the formula weight of this thing. Okay, so sodium is 22.99 plus we have 1, 2, 3, 4, 5, 6, 7 carbons. So that's 7 times 12.01. There's 2 oxygen, so that's 16 times 2. And there's 5 hydrogen. That's 5 times, and that's 1.008 in the periodic table in the book. Anyway, oops. Close that off, and that's all in Daltons or AMU, whatever you prefer. Okay, that gives us a total of 1.4226 times 10 to the negative 2 moles. Okay, there's that one done. Okay, so and then let's also get the moles of of benzoic acid, and that is nearly the same. H5COOH instead of the Na. All right, and we're going to get that. I'm just going to draw a line there. We're going to get this exactly the same way. Mass over formula weight. And in this case, we had 2.47 grams. And this is going to be, so now we have 7 carbons again. Right, 7 by 12.01 plus 2 oxygens. Right, 16 times 2 plus, and now we just have 1 extra hydrogen, 6 times 1.008. 08. So the square bracket, and again, that's all U. And this one gives us 2.0226 times 10 to the negative 2. Okay, so a couple more of this than of this here. So now let's clear all this up now that we have those values. Yeah, I've got them written down over here, so I'm gonna wipe this whole thing out, and I'll write up our equation up top now. So we're gonna have the acid in the reactant. So that's gonna be A6H5, right? COOH, right? Aqueous, obviously. And that is going to dissociate into 5, right? There's the benzoate, also aqueous, and the hydroniums. Okay, so we don't have to worry about the sodium in this business, because the sodium is sodium's a conjugate ion from from sodium hydroxide, so it's not going to be influencing the pH anyway. So we can just count the initial concentration of the sodium benzoate here. We don't worry about the sodium ions themselves. So the initial sodium benzoate, that was 1.4226 times 10 to the negative 2. Right, hydroniums are going to be nil, and benzoic acid, we had 2.0226. 26 times 10 to the negative 2. Okay, so more over here than over here. So Chatelier says we're gonna go right instead. So we're going minus x plus x plus x. Close enough, I suppose. Okay, and then we can calculate our Ka expression from here. All right, so we have Ka equals, and we're gonna have this thing times x up top. That's gonna be how do I want to write that? Yeah, let's just write it like that. 0.14226 plus x times x, and that's over, do this one the same way, 0.226, and this is going to be minus x. All right. And we have we were given a Ka value here, so this was 6.3 times 10 to the negative 5. Okay, so 6.3 times 10 to the negative 5. All right, we're going to multiply that by 0.020226. Should we assume x is small? Yeah, why not? Why not? And then we'll divide this by this concentration here, and that'll isolate the x up top. 226. Because assuming the x's are small just means that we're not concerning ourselves with the ones that are added or subtracted, but obviously multiplied if it's small is going to make a huge difference, so that one stays. All right, equals x, and this is going to evaluate to 3 times 020226 divided by 426. So I've got I have x equal to 8.957. 957. Oh, sorry. Those don't look anything like they were supposed to. 9. It's even worse. 57. All right, by 10 to the negative 1, 2, 3, 4, 5. And that should be close to an okay approximation. Let's just check. Divide it by our initial 226. And I've got 0.4%, so we're fine. So the x is small approximation is valid, so we can go straight to the pH. And pH is going to be the negative log of that result that we just got for x, right? Because x is equal to the hydronium concentration up here, so we can just take the log straight away of that thing. 957 times 10 to the negative 5. There we go. Doesn't actually look half bad. And let's see what we get. Negative log of 58957. And I got a pH of 4.05. 0.05. And there's our final answer. It's the pH for that common ion problem.